Hi everyone, today we are going to talk about lesson 3.2, which is the characteristics of quadratic functions. We are going to discuss three different formats that a quadratic function can be written in, and the first is vertex form. We're going to focus on vertex form first because we used that in the last lesson to do transformations to our quadratic functions, so you're already familiar with it, so this should be review. The equation for vertex form of the function is that f of x is equal to a number a multiplied by the quantity of x minus h squared plus k, where a, h, and k are numbers. We also talked about the axis of symmetry last time, and we used that to plot the left side of our graph. So the axis of symmetry is located at the line x equals h. And remember that because of the negative sign in the vertex form of our equation, the h is the opposite of the sign that you actually see in the equation. We also talked about being able to very easily pick out the vertex from the vertex form of the equation, and the vertex itself is at h comma k. Again, remembering that h is the opposite sign of what you see in the equation. Let's talk about intercepts, both x and y intercepts. Because the vertex form of the equation is set up to readily identify the vertex, it's not easy to find the x and y intercepts from this form of the equation. We would need to use another method for that. Let's talk about standard form of the equation next. So standard form is in the format of f of x is equal to ax squared plus bx plus c, where a, b, and c are numbers. In order to find the axis of symmetry, we do have to do a small calculation. That calculation is that the axis of symmetry, that line is x is equal to b over 2a, and it's the negative of that. Taking the axis of symmetry, that gives us the x value of our vertex, so we can plug that in as the x value of our vertex. Knowing the x value of our vertex, we can take that value and plug back into our original function up here everywhere that we see x, and we can solve for f of x or y. So we plug in x to find y. That means that this value right here is used as our y value of our vertex. Let's talk intercepts here. The x-intercept still can't be identified readily from this method, but it is set up to very easily find the y-intercept. Our y-intercept is equal to 0, c, where c is the constant at the end of our equation. Finally, we have what is called the intercept form of the equation, and that takes the form f of x is equal to a times the quantity of x minus p, and then times the quantity of x minus q, where a, p, and q are numbers. Our axis of symmetry is again a little bit of an equation to solve. X, the line of symmetry, is equal to p plus q over 2. Notice, just like in vertex form, in the parentheses we have some negatives here. So p and q are the opposite signs of what are in the equation. Once we know the x value of our vertex, we can again take that x value and plug into our original equation right here, everywhere that we see x, and we can find our y value. So again, plug in x to find y. All right, let's talk intercepts. This is called intercept form because it's very easy to read the x-intercepts off of this form, or the places where it crosses the x-axis. Those values are at p, 0 and at q, 0. Again, remembering that there's a negative built into the equation, so the sign that you see is the opposite of what the actual value is. Y-intercept, not easy to find. We would need to use a different method, such as the standard form of the equation. Let's go ahead and look at an example where we have written the same exact quadratic function. In other words, all of these would graph the same if you graph them in Desmos, but we've written it in all three different forms. Starting with our vertex form, the one that you're most familiar with, we can pull out the a, h, and k values that you see here. A is 4. H, since I see a positive in the equation, h is actually negative 1/2, and my k value is negative 49. We can recall that our axis of symmetry is that x is equal to h, and so our axis of symmetry is at x equals negative 1/2. Our vertex, if we take the negative 1/2 and we plug that into our original equation right here where we see x, so plug in negative 1/2, you will see that you'll have a negative 1/2 plus 1/2. This entire term goes to 0, and what you're left with is negative 49. The same equation written in standard form would look like this, where we have an a value of 4, a b value of 4, and a c value of negative 48. Our axis of symmetry, remember that we have a little equation that we have to plug into, where our axis of symmetry is the line x is equal to negative b over 2a. So that's negative 4 divided by 2 times 4, or a negative 1/2. That matches what we came up with the vertex form, which should make sense because we're talking about the same exact function. The other thing that you might recall is easy to determine from this form of the equation is the y-intercept. It's simply an x value of 0, and the y value is our c value. So our y-intercept is 0, 48. Finally, let's look at our equation in intercept form. So our equation looks like this, where we have an a value of 4 still, a p value of negative 4, and a q value of positive 3. Remember again that those negative signs are built into the equations inside those parentheses, so p and q are the opposite of the signs that you see. We have a little equation in order to find our axis of symmetry, and that equation is that x is equal to p plus q divided by 2, so the average of those two values. So taking negative 4 plus 3 and then dividing by 2, we, for the third time, get an axis of symmetry at x equals negative 1/2. Remember that the other thing that's easy to figure out from this version of the equation is the x-intercepts, where y is equal to 0 and we are crossing the x-axis. Those occur at negative 4, 0 and at 3, 0.